Oh, wait, you're listening?
Okay.
All right.
Okay.
All right.
You're
Listening
to Radiolab.
Radiolab.
From
WNYC.
See?
Yeah.
The one thing I have to apologize for is I'm still kind of stuffed up, so you're going to hear noses being blown frequently, but I will do it off mic.
Oh, that's okay. I'm not particularly sensitive to nose blowing, so...
This is Radiolab. I'm Lula Miller, and today is day 3 of our week of sharks.
Do you feel good? You in a zone? You feel...
I'm in a zone.
And today's story comes to us from producer Becca Bressler.
Yeah. Well, I do think that this is maybe the most interesting story I've ever worked on.
Ooh.
And it's actually kind of weirdly fitting that you're sick right now.
Okay.
But okay, so first couple of episodes, we were swimming in the shark-infested waters of Australia. Today, I'm going to take you somewhere different.
Great. Where are we going?
Buckle up.
Buckled.
We are going to Wisconsin.
Have a nice day.
Okay. Midwest landlocked? This is not where I'm thinking you're going to encounter a shark.
No, as I wasn't expecting it either, but I was going to see this scientist. Hey, Aaron? His name's Aaron Matthew LeBeau. How's it going?
Good, how are you?
And he
I'm the least sciencey person I know.
has a kind of funny way into this.
I originally went to University of Arizona as an undergrad to play football, have fun, and party.
Took a chemistry class.
Absolutely fell in love with chemistry. And then from there on, I just became a scientist.
But did you party too? Important question.
I partied a whole lot, yes. I consumed my body volume in tequila many times.
Anyway, he gets his PhD.
Dr. LeBeau.
Dr. LeBeau ends up at the University of Wisconsin in Madison, where he has his own lab. So can you say where we're headed right now?
We're headed to my laboratory on the 7th. Ooh, I can't say that.
A secret lab.
Ooh.
Oh, we're going to hop on the shuttle now.
Yes.
Okay, so we took a bus about 5 to 10 minutes across campus.
So our stop right here.
Got off and walked over to a nondescript location.
I can't tell you where it is.
I won't ask again, I swear.
Site.
Went into this building and down a flight of stairs
If I can
into the basement. The room we're in right now looks kind of empty. It's into this big abandoned lab.
It was, I think, last used about 15, 20 years ago.
Empty cabinets, dusty black counters.
It's been abandoned since.
And then we turned around a corner into this other room where, oh, whoa, in the middle of it. Can you just describe to me what I'm looking at right now?
Yeah, you're looking at a state-of-the-art 7,000-gallon saltwater tank.
There is
A huge, huge, huge fish tank, basically.
an above-ground pool of, whoa, sharks. Oh my God. So how many sharks are in here? 5 sharks.
So you're in like an unmarked bunker with a pool full of sharks.
Yes, specifically nurse sharks.
Nurse sharks.
So
okay.
they are,
They're the littler ones?
so these ones were only about like 2 feet long.
But these guys are also not full-grown yet. In the wild, you have nurse sharks that are, 8, 9, 10 feet long.
Big. Okay.
And they look shark-like, but maybe not exactly what you're thinking.
They don't have the large jaws like a great white do.
They've got these tiny little mouths that,
Suck up food.
that's the sound of the suction. They also have whiskers, so
Oh.
some people call them cat sharks.
Okay.
But maybe most importantly, these sharks,
These are like swimming fossils.
they're ancient.
Ooh.
They come from a line of sharks that date back,
400 million years ago.
Ooh. Huh.
and hidden inside of them, scientists like Aaron believe there is this very ancient key. A key that could unlock our ability to fight off some of the deadliest threats we face on Earth. And that's really the story that I want to tell.
Yeah. Okay. Keep us going.
Okay, first, to get to Aaron's lab, we have to go from sharks
Sounds kind of strange when you've got the headphones on actually talking.
back to us.
I can't hear her now.
Hello?
Oh, there we go.
Hi. Hey, Caroline.
Hi, Becca.
Because to find this key, scientists first had to figure out something very deep and mysterious about humans. So I guess to just start this off, Caroline, can you tell me a little bit about who you are and what you do?
Yeah, sure, Becca. So I'm Caroline Burrell. I've always been passionate about life sciences, kind of set off my career at university studying biochemistry, then moved on to a PhD.
She runs a biotech company now.
Yeah.
And she has spent a ton of time researching and studying the immune system, and in particular,
Antibodies. Oh, Oh, they're formidable.
One of the most incredible parts of our immune system.
That are protecting us non-stop, 24/7 from the onslaught of what's going on in our daily lives.
So let's say you're out in the world, like at a park or something, and some guy coughs right in your face. And let's say a little bit of that cold virus he has goes into your body. And what happens is
Just wizardry.
these immune cells show up, and each one of them starts pumping out
Hundreds of thousands of these antibodies.
so that quickly
Your body is full of this army
of billions and billions of antibodies that are specifically designed
of
for
their target.
that virus.
And an antibody
It looks like a big Y.
So this army of Ys
hone in.
surround this virus,
And the two arms of that Y
reach out and latch onto the virus
just kind of hold on to it.
Really tightly.
until other cells can come in and kill it.
It blows your mind. It really does.
Because Caroline points out, it's not just that your immune cells are doing this for a virus. It can be something
Like a fungus, like a bacteria.
maybe a parasite, a toxin,
You know, you may get a small cut, you may get dust in your eyes, you may get something going on.
whatever it is.
You can make antibodies against almost anything that's out there.
Tailor-made, bespoke antibodies for anything.
Anything, even if it's never existed in our environment before.
Wait, what?
Yes, even for things that don't exist, your immune cells can make antibodies for it.
That is so cool.
It's amazing, actually. Sorry, it almost sounds religious. The Pope just died, and I don't know.
So these two new voices you hear,
Yeah, I'm Helen Dooley.
one is Helen Dooley, the other
Martin Flanagan.
Martin Flanagan.
I work for the medical school here at University of Maryland, Baltimore.
So does Martin.
Almost 30 years at Maryland.
And the two of them, they study the evolution of immune systems.
To try and understand how the immune system that we have evolved.
So this is where the story really picks up.
Okay.
Because Helen and Martin explain, when we first discovered antibodies, there was this real puzzle as to how they could even exist, how an immune cell can even do what it does, how it can
Generate billions of different antibodies.
like that's something a cell shouldn't be able to do.
It didn't make sense.
Because if you think about, say, a hair cell, it has DNA in it that tells it how to make hair.
And we thought that was the same with antibodies, but then it turns out if you can make antibodies against all these different things, you would need so much DNA in your cells that the whole system just wouldn't work.
Your cells literally can't contain that much information.
Yeah, so then in the 1970s, the group was looking at antibody genes, the genes that encode antibodies or part of antibodies.
And while they were looking at the genes in this immune cell,
What they realized
was that in it,
It was something really special.
there seemed to be a gene in there that was going around and snipping up DNA and then shuffling those bits and then stitching them back together.
and what that meant was the cell could mix and match.
Different pieces of DNA.
And by virtue of that,
The immune cell could create billions of different combinations in order to create
billions of different antibodies.
It just is incredible. It's incredibly complicated, but it's just amazing.
it's a sort of magic
That bit is genetically just wizardry.
that no other cell in our body can do, just our immune cells.
But when they saw that, they thought, okay, that's interesting. And of course, the beauty of academia is that they will then dive down and they will start asking more questions, trying to answer more questions, researching it. And that really was the start of the whole thing.
Because what scientists wanted to know now was, when did this happen? Like, when did this one cell, the immune cell, suddenly get this superpower? So for years, what you had were groups of scientists, like this team down in Miami,
Basically looking at the animals that were there in the waters off Florida and taking blood samples,
looking for
antibodies.
evidence of this superpower and when it first showed up.
So they were basically going back to other creatures to see if these antibodies were present or not at that point in time.
So the idea being they would take blood samples from these animals, comb through whatever it is they find in there,
And see if any of them kind of had the same weight or characteristics as a human antibody.
Classic Y.
right, the Y shape.
So
First up,
birds.
birds split off on the evolutionary tree about 300 million years ago.
Okay.
Turns out researchers already knew this, but birds have the little Y, antibody.
Yes.
And so
Next step,
they went back
To reptiles.
320 million years ago.
they have antibodies.
So
Back further.
Amphibians,
about 360 million years ago.
Antibodies.
Even further back,
To fish.
430 million years ago.
antibodies again.
450 million years ago.
Sharks.
They have them too. And then it stopped.
So animals without backbones. Everybody would know the sea urchin.
Which is about 500 million years old.
When you look at those creatures, there are no antibodies.
What they have are much simpler immune cells that can defend against far fewer things.
That's right.
And so sharks are really...
Wait, hold on. Literally,
yeah.
sorry. I have to stop talking. I have to blow my nose because I can't hear you.
Oh,
when I
yeah,
do.
sure.
Okay. Like, are there antibodies in that snot?
I think so. I mean, that's not really...
Okay, keep going.
Okay. Anyways, so sharks are the oldest living things on Earth that have an immune system like ours. It's like pretty much where our immune system began.
Does anyone know why? Like, why were sharks the place where this immune system first showed up?
Yeah, so around that time,
There were some interesting things that happened 450 to 500 million years ago.
Through the randomness of evolution, the branch that had sea urchins suddenly split. And now you started to have animals
A
with
backbone.
a tail,
fins,
a head,
a jaw, and teeth,
a large brain.
complex neuronal circuits.
You get fish that lead to bigger fish, and eventually
The shark.
a predator that the world has never seen before. And once you have a predator, pretty much everything else becomes prey.
And there is going to be a ratio that you have to maintain.
Like there has to be some sort of balance.
Yes, you can't have too many predators with the prey.
If you did, all the predators would eat all the prey. There would be nothing left to eat. And so what you see, Martin says, often in nature,
Is predators in general don't have very many offspring.
they have fewer babies. So it maintains this balance. Now,
This is heavy speculation, okay?
okay. But Martin's theory is if you have fewer offspring, then those offspring will need every defense they can get.
Such as
Little Y-shaped molecules with 2 arms.
antibodies.
And what scientists piece together is that right here, around that split, when you have jawed predators with teeth, that simple immune cell in sea urchins,
The idea is it was this lucky event.
where this little rogue piece of DNA that you can find in all animals just so happened to make its way into that simple immune cell and tweak one of its genes.
and give it this property where now it can mix and match different pieces of DNA.
The ability to generate billions of different antibodies.
It's almost like the way that I think about it is the spider that bit Peter Parker, like bit this immune cell, this like proto-antibody, and suddenly you have this superhero immune cell that can defend against anything.
That has come in from the outside.
That's one theory. On the phone, you said there are others, and you very funnily suggested they're all wrong. But do you know what they are? Are there any other big theories out there?
I can tell you one.
Okay.
One.
Okay.
So this one's called the Jaws hypothesis.
Jaws. So once jaws emerge, you have these species that can eat things with bones. They can munch on their bones.
And the bones during digestion could cause scarring of the digestive tract and therefore, cause potential infections.
So some people think it evolved because you are now exposed to so many more things and you need to fight off those different infections that could arise.
Okay. Right. That makes sense. Like the more opportunities there are to be exposed to things that kill you, therefore defeating things that kill you must be better.
Right, exactly. But the funny thing is that one scientist started to really put this whole puzzle together of how we got this immune system. When they found it in sharks, they were just like, meh, Okay.
The prevailing thought was that sharks had a very simplistic version of our immune system, almost like the Model T Ford of our Ferrari immune system.
Like we can make antibodies in 3 to 4 days. Sharks?
We're looking at 3 to 4 months.
They thought it's not that efficient.
Its immune responses are very slow.
It's like 400 million years old. Of course it's not as good as ours.
Yeah.
But that idea would...
Sorry.
It's okay. That idea would be proven to be very, very wrong. Dead wrong. We'll be right back.
Stick with us, partner. Lulu, Radiolab back with Becca Bressler, sharks, and the things inside them that keep them from getting sick.
Immune systems are just insane. I mean, just the fact that we can create antibodies against things that don't even exist in nature.
I love that.
What?
It's so cool.
Yeah.
Okay, wait, so let's zoom way out. Okay, so just a recap.
Yes. Go ahead.
We meet a guy named Aaron. He takes you to a bunker. He's curious in immune responses. We're learning about probably there was this big bang around 500 million years ago that goes hand in hand with complexity. And now, yes, where are we going next?
Yeah, so where we left off, scientists had discovered sharks have an immune system, but thought it was pretty simple compared to ours.
Right.
The Ford to our Ferrari, as Helen put it. But that all started to change in the late 80s when Martin showed up.
I got my first job in 1987 at the University of Miami.
In an immunology lab.
And there they worked on sharks, obviously.
Looking at their immune cells that make their antibodies.
We wanted to isolate the cells from the shark and then study their functions.
So when they started playing around with these cells, they saw that, of course, they made shark antibodies.
Right.
Obviously.
That's right.
But then he also saw this other thing.
That the shark was making.
That sort of looked like an antibody.
But a little different.
It had the same Y shape, the 2 arms, but it was smaller.
And that was weird.
Hadn't seen that before.
No.
So he grabs some of these itty-bitty Ys, puts them under a microscope.
It's called electron microscopy.
And what he sees is that the arms on these things
were highly mobile.
Like really flexible.
They move from 0 degrees to 180 degrees. Like a cheerleader with her arms out.
And this was something completely new. We've never seen it before in a shark, in us, in any immune system.
Yeah, it just smelled to me like this was something interesting.
I think that's kind of where I came in.
So over the next few years, Helen and Martin, they would do these experiments where they would take something that didn't belong in a shark, put it inside of it, and watch these little Ys surround this thing in the shark. And with their flexible arms, they would get into it and they would hold it super, super tightly.
Just amazed by it.
And the two of them were like,
it's amazing.
Oh, these are antibodies. These are like a whole new type of antibody.
That was fantastic.
So when you discovered this, did you understand the implications of it?
No, I probably should have. I probably should have, but
So Martin, he's just seeing something new.
Basic science. He just saw a thing.
He just saw a thing. However, because these antibodies are so tiny and so flexible and so sticky, scientists today actually think that they might be the key to what's the word I'm looking for? Not solving, but like the key to curing cancer.
In humans?
In humans.
What?
Yes.
Wait, what? How?
Okay, stick with me. So, can I take photos or is that a no-no?
Oh, absolutely.
Okay, this is actually where I want to take us back to Aaron's lab.
In a basement in Madison.
In a basement in Madison.
The big boy there is Mr. Stamper.
Because Aaron is one of the few people who is developing these antibodies. to try to cure cancer. So we've got nets out, and you're using the nets to
corral the sharks in a place so we can catch them with a big net here.
And so how this works is they catch a shark. So we got a shark. Oh, should I move? I should move. They dump them in this bucket full of anesthesia to put them to sleep. If you weren't putting pressure on the top, would it like fly out of the bin?
Yeah, it would fly out of the bin, yes.
And once it's out,
he's out.
Okay, we got a sleepy shark. They inject a little piece of the surface of a cancer cell into that shark.
Is this any kind of cancer? Is this a particular kind of cancer cell?
Prostate cancer.
This is prostate cancer that is resistant to all forms of current chemotherapy.
Okay.
And where are you putting this injection?
Last time we did the left fin, so this time we're doing the right fin.
And once they have this little bit of a cancer cell in the shark,
You have a huge immune response.
the shark starts producing millions of antibodies. And then
You deliver repeat booster shots of these.
they do it again and again.
For a terrible analogy,
Getting these sharks to make these antibodies over and over.
it's kind of like playing basketball. So if you practice more, you're a better shot. Same with the immune system.
This is immunotherapy, training antibodies to be really good at latching onto a target. Because once you've trained it to, say, latch onto a cancer cell, you can attach a little, like, radioactive bomb to the antibody.
We basically use the antibody as a delivery system to efficiently deliver
This little bomb
to the cancer cell.
to kill it.
Yes, correct.
And this is also something we do with human antibodies, even for, like, certain types of cancers. But sometimes human antibodies are not very good at sticking to cancer cells.
But shark antibodies,
With those small, flexible, wiggly arms,
they can essentially do molecular yoga and adopt many different shapes. And by adopting many different shapes, they can get into nooks and crannies of targets that human antibodies can't access.
like certain parts of cancer cells.
Yes.
So Aaron said that it takes about 2 months to train these antibodies, and that the first time they went to test one of these things,
Oh, this is about 2 years ago.
they took the shark antibody, injected it into a mouse with a tumor,
Through the tail vein of the mouse.
did some fancy imaging.
And I thought, wow, I've never seen this before. Within a day, we saw the antibody homing to the tumor and just collecting there.
They were just latching on to these tumor cells and nowhere else. They didn't find it anywhere else in the body.
Stop.
It like laser focused right to the tumor.
It moved like we think sharks move, like where they like detect
Stealth. and- yeah,
like
totally.
detect a drop of blood and then boom. What?
Were you surprised by this, or were you expecting these results?
I've been doing mouse radiology for 20 years and it knocked my socks off.
Really?
Honestly, yeah. I've never seen an antibody work that well.
And they would follow up that study with another, where they attached a little bomb to the antibody, and it worked.
Wow.
They eradicated the cancer.
Wow.
Do you see any immune response to the antibody? Because I guess I would just expect that a shark antibody for a mouse is like a foreign invader that the mouse would then, produce antibodies against.
Yeah, so for some reason, we do not see an immune response. And we don't really know the concrete reason why. We've done studies in mice and other rodents, and there are a few other people working on shark antibodies in the world. And that's one thing that we all talk about is how we don't see an immune response against them.
I mean, I think that's so fascinating because, like, even for a human, if you're growing a fetus that's half genetically yours, your body will launch an immune response. Like, that's the purpose of the placenta and the sort of struggle of pregnancy. I just can't even grasp that a shark antibody would not trigger an immune response.
Yeah, it's one of those things that you have to see to believe, and we've seen it many times. And we're going to do a primate study. We're going to do an imaging study to see where this antibody goes in the body of a non-human primate. And then we're going to also repeatedly dose the primate with the antibody to see if we do generate an immune response against it. And my hunch is we won't see any antibodies against our shark antibody.
Wow.
Yeah.
I mean, I don't know if we should do any meaning making here, but can I just
Yeah, go for it.
I mean, I think so much of what we learned in the first couple days of our week of shark is like that a monster, it maintains its fear by being unknown, unseen, sort of other. And there's something like, if at the molecular level we can embrace these things as us, there is like profound molecular entanglement. Like they are so much closer than I ever thought.
Yeah. Yeah. I mean, like that entanglement is precisely why they can heal us, you know?
Yeah.
Like these animals that we don't even want to share the water with because we're afraid that they'll harm us could actually save us. Oh, wow. So each shark you're using for different...
Yep. Each shark is fighting a different disease.
And not just from cancer.
The shark we have right here is being injected with proteins that are expressed when we sense pain.
So with one of those sharks, they're developing antibodies against pain receptors that you find in humans. So they can help us find where that pain is in the body.
Wow.
We had one shark that was pumped full of fentanyl to make anti-fentanyl shark antibodies.
They're developing antibodies against lung cancer, breast cancer, Alzheimer's.
Okay. Wow. So you're saying just like there's this burgeoning hope of potential for what these antibodies could heal or make clear.
Yeah.
Yeah.
Yeah, what do you think about that?
It's pretty cool. It's beautiful. Yeah.
Do you think that sharks, like these antibodies, could be the most powerful tools we have to fight these diseases?
Never say never, potentially.
Potentially.
I like to think that the future is shark, personally.
The future is shark.
Yes.
I feel like that's a good place to end.
The future is shark.
This episode was reported by Becca Bressler. It was produced by Becca Bressler and Matt Kilty. Original music from Matt Kilty. Sound design contributed by Matt Kilty, Jeremy Bloom, and Becca Bressler. Fact-checking by Diane Kelly and edited by Pat Walters. Special thanks to Gihan Gunrasnan, Jay West, Kendall Ott, and the entire LeBeau Lab at the University of Wisconsin-Madison. Go Sharks. Not actually their mascot, but maybe it should be. One more thing, we want to give a big thanks to everyone out there who is a member of the Lab, our membership program. Your support makes big projects like this possible, and we are so grateful. And if you aren't a member or you've been thinking about giving more, this is a great moment to take the plunge because if you join or re-up right now, you'll receive a very cool gift, a limited edition Week of Sharks hat designed by the awesome Maine-based artist and surfer, Ty Williams. It's so beautiful and fun, and it gives you a chance to show the world you support public radio in the form of Radiolab, but also support seeing sharks in a new way. The Shark Hat is available to everyone who joins the lab this month, even for as little as $7 a month. You can join at radiolab.org/join. Existing members, check your email for details, and thank you so much. Swim on back over to us tomorrow morning, where there will be yet another episode about sharks surfacing in the Radiolab feed.
Hi, I'm Georgina, and I'm from China. And here are the staff credits. Radiolab was created by Jed Abumrad and is edited by Soren Willa. Lulu Miller and Latif Nasser are co-hosts. Dylan Keith is our director of sound design. Our staff includes Simon Adler, Jeremy Bloom, Becca Bressler, W. Harry Fortuna, David Gable, Rebecca Lex, Maria Paz Gutierrez, Sindhunanam Sambandan, Matt Kilty, Annie McEwen, Alex Neeson, Sarah Kari, Sarah Sandbach, Anissa Vitsa, Ariane Lack, Pat Walters, Molly Webster, Jessica Young, with help from Rebecca Rand. Our fact checkers are Diane Kelly, Emily Krieger, Anna Bujol Mazzini, and Natalie Middleton.
Hi, I'm Daniel from Madrid. Leadership support from Radiolab Science Programming is provided by the Simons Foundation and the John Templeton Foundation. Foundational support from Radiolab was provided by the Alfred P. Sloan Foundation.